Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing solid state. Under that I was discussing relationship between the nearest neighbor distance and the age of the unit cell. Nearest neighbor distance, that is a small d, and age of the unit cell is a small a. Then for this I have discussed a relationship between these two in case of simple, body centered and face centered. Now I will continue further. This is the relationship between three. 3 means first is atomic radius, that is a small r, and second is d. D is the nearest neighbor distance, a small d, and age of the cell, that is a small a, means a small r, atomic radius, and this age, a small a. Then here r and d, that is r is equal to d upon 2, a small d, that is the nearest neighbor distance. Then here relation I am telling you, that is a relation between r and a, and here there is no relation between d, but r and d are related. R is equal to d upon 2, means half d, but here directly relation is between atomic radius r and age of the unit cell, a small a. Then in the case of simple cubic unit cell and body centered and face centered cell, all are the unit cell, simple, body centered, face centered. In all these three, how a and r are related, I am telling you. Then in the case of simple unit cell, in simple unit cell, r is equal to a upon 2. R is equal to a upon 2. Here I want to tell you, I am reviewing the chapter. Correct? Already I have discussed details when I was discussing 11th and 12th that time. And now I am reviewing the chapter. And now in the case of simple, r and a is related. R is equal to a upon 2. This is in the case of simple unit cell, r is equal to a upon 2. In body centered, r is equal to under root 3 by 4 into a, upside a is there. R is equal to under root 3 divided by 4 into a, upside a small a, that is the age. If you put the value of root 3, then you will get 0.433 a. Correct? Then in the case of body centered, r is equal to 0.433 into a. And in case of face centered, r is equal to a upon 2 root 2. A upon 2 root 2. Then after putting the value of root 2 and simplifying, you will get 0.3535 into a small a. Hence, in case of simple unit cell, r is equal to a upon 2. In case of body center, r is equal to 0.433 a, and In case of face-centered, it is 0.3535, means it is decreasing. Correct? R is equal to A upon 2, means half. Half means 0.5. And in body center, it is 0.433, 0.433. And in a face center, it is 0.3535. Then it is decreasing. Now expression for density of a cubic crystal in terms of its age. These all are important and it is asked in examination. Sometimes before when you want to calculate density of the cubic crystal, then that time this relation is used. Then now I am telling expression for density. Density is represented as rho, just like a small p, rho. Expression for density, that is a rho of a cubic crystal in terms of age. Age means here a small a. Then rho is equal to Z into M divided by AQ into N0 into 10 to the power minus 30 gram per cubic centimeter. Here actually should not be afraid by this big expression. You know that density is equal to mass by volume. Simple formula. Density is equal to mass by volume. Then here you want to calculate mass. Then for the mass you are writing Z into M. Here Z is the number of atoms present per unit cell and M is the atomic mass of the element. Then atomic mass you are knowing of one atomic mass of element. That is for one atom. Then for number, we multiply by number of atoms present in per unit cell, present in a cell, then you will get a total mass. And that is the Z into M. Z is equal to number of atoms. And one atom mass is capital M. And total mass will be Z into M. Then M value are knowing, mass, now divided by volume. Then volume formula, you know, A into A into A. For a cube, length into length into length. Correct? Length cube, you know. Then here length is equal to A, small a. Hence in the here you have written AQ. But this AQ is you have to multiply by N0, means Avogadro number, because this volume, AQ volume is only for one atom, Then for N0, Avogadro number, what will be the total volume? For volume of one atom is AQ. Then for Avogadro number, how much? Just to multiply by Avogadro number. Then Avogadro number is 6.02 into 10 to the power 23. Okay, in formula you write only N0, Avogadro number. Then down you have written AQ into N0 into. Now you have to just know in a gram. Then mass, if you will consider mass, these things, if you will consider in a gram, and one more thing here, you have to multiply by 10 to the power minus 13 down. Avogadro, this total volume means volume of one atom. Into Avogadro number into 10 to the power minus 30. 10 to the power minus 30 you have to multiply. Then down you will get full volume of 1 mole. Or you can say that in a unit cell, that how many atoms are there, then total volume of all atoms correct? Then you have multiplied by 10 to the power minus 30. Then actually for one atom volume is very less, 10 to the power minus 30. That's why you have to multiply. AQ total volume I have written, but for one you can say unit atom, that value is fixed. That is, the volume is fixed, 10 to the power minus 30. Then after multiplying by this, you will get a total volume. Then total mass you have written upside, total volume down. Then rho, that is the density, is equal to mass by volume. Then its unit is gram per cubic centimeter, gram per cubic centimeter, correct? Then this is the density. Then this formula is very important, and you remember what I told you in that way. Density is equal to mass by volume, then mass is equal to Z into M, and volume is equal to AQ into N0 into 10 to the power minus 30. 10 to the power minus 30, 30. Then you will get unit, that is a gram per cubic centimeter. Gram per cubic centimeter. Then rho is equal to Z into M divided by AQ into N0 into 10 to the power minus 30. For cubic crystal of ionic compounds, Z is the number of formula units. Again you remember, for a cubic crystal of ionic compounds, Z is the number of formula units present in unit cell, and M is the formula mass. Just simply you multiply, you will get a total mass. Now I am going to tell about the silicates. What is the silicates? Then silicates are the compounds having SiO2, silicon dioxide. Silicon, just like a carbon dioxide, CO2. Here it is SiO2. Then silicates, many silicates are there. Then silicates are the compounds having SiO2 tetrahedra. Its structure is exactly tetrahedral. Then silicates are the compounds having SiO2 tetrahedra as the basic building units. Only this will be repeated many times. They are linked by corners and never by edge. This you remember. Actually repetition will be there. Same unit will be repeated, then it will become a big. Then they are linked by corners and never by edge. This you remember. Never by edge. They are linked, all units are linked by corners. Now types of silicates. There are 6 types of silicates, and all silicates are very important. Okay, and so listen carefully. All 6 are very important. Question is asked. First, orthosilicate. Orthosilicates. Here also this types of silicate. First I am telling you orthosilicates. Then orthosilicates, different in this orthosilicates also many type of will be there, but all are called because the structure will be the same, and so it is called silicates, orthosilicates. All are orthosilicates. Just like you can tell anything you are telling rice, different type of rice is there. Pulses, different type of pulses are there. Vegetables, different type of vegetables are there. Like that, in that sense you can take. Then orthosilicates, which contain discrete SiO4, means very small. Discrete means very small. Which contain discrete SiO4 tetrahedra. Example is zircon, Zn SiO4, Z, zircon ZnSiO4 means with silicate zinc will be attached. Silicate of zinc, that is called zircon. Question is asked. And other example is forsterite. Forsterite means Mg2SiO4. Here magnesium is there, 2 magnesium is attached with silicate. Mg2SiO4. SiO4 is common. This is called forsterite. F-O-R-E, forsterite. Question is asked. All examples directly in general examination, competition also these are asked. Then I told the example, 2 examples I told you for orthosilicate. First is the zircon, that is a ZnSiO4, and second is forsterite, that is the Mg2SiO4. Then first I told first type is orthosilicate. I told the example also. Now second type, pyrosilicate. There are total 6 types. Then second type is pyrosilicate. Pyrosilicate, in this silicate, 2 SiO4 tetrahedra shares one corner. Here you remember, 2 SiO4 tetrahedra. 2 SiO4 tetrahedra share one corner. In one corner, 2 SiO4. Example, that is the thortebhetite, Thorte, thorte, Veitite, thortebhetite, and its formula is Si2O7. Se means selenium. Selenium. Si2O7. With selenium, Si2O7 is attached. And other example is hemorrhite. Hemorrhite. Hemimor. Hemor. Hemimor. Hemorrhite. Phite. Its formula is, you can say, little big, but both are joined, both are of zinc molecule only. Okay, that is the formula is Zn3Si3O7, and with this only other unit is attached, that is a ZnOH2 H2O. 2 molecule is attached. First Zn3Si3O7 and other unit attached it ZnOH2 H2O. This is called hemorrhite. Then 2 example of pyrosilicates I told you. First is thortebhetite, and formula is Si2O7 with selenium, 2 molecules of 2 atoms of selenium, Si2O7 is attached. Another example I told you, hemorrhite, that is a Zn3Si3O7 and other unit attached is ZnOH2 H2O. Now third types, that is the cyclic or ring silicate. Cyclic silicate or ring silicate, both are same. Here what happens in a cyclic or ring silicate, 2 corners are shared to form a closed ring. 2 corners are shared to form a closed ring. Example, beryl, BERYL. Question is asked everywhere in medical engineering, everywhere this question is asked, even in general competition also. Beryl, BERYL. Beryl is, you can say, cyclic or ring silicate. its example is beryllium. Actually, it is a molecule of beryllium, aluminum, and silicon. Its formula is Be3Al2Si6O18. Means here 4 elements are, it is a molecules containing 4 elements: beryllium, aluminum, silicon, oxygen. Si6O18 is telling about actually silicate. It represents silicate. Si and O always represent. Their atom may differ, number of atoms may differ, but they are representing silicate. Then here Be3Al2Si6O18. This is actually beryl. Now next silicate is chain silicate. Chain silicates. What is a chain silicate? Then chain silicate, here 2 corners are shared to form a long chain. There you have seen previously in cyclic, 2 corners are shared to form a closed ring, but here 2 corners are shared to form a long chain. Examples are pyroxene, and second example is asbestos. Both are common. In real life also you are using asbestos for making the roof, asbestos roof. Then pyroxene and asbestos both are its example. Pyroxene, Pyro, pyro, that is related to fire. Pyroxene, Xenes, pyroxenes. And second example is asbestos. Now next type is a sheet silicate, fifth type. Sheet in the form of, you will get silicate in the form of sheet. Here 3 corners are there. Till now 2 corners you have seen. 2 corners. In cyclic also 2 corner, in chain also 2 corner. Now in sheet 3 corners. 3 corners are shared to form a 2-dimensional sheet. 2-dimensional sheet means length and breadth. Height will be very less. Length and breadth more. Height will be just like you can say one line you are drawing. 1 centimeter breadth, 10 centimeter long length. Correct? Height you are not giving importance. Negligible. Just like a paper sheet. Thickness is negligible, very less. Length is more, breadth is more. Then that is actually called sheet. Then here 3 corners are shared. In sheet silicates, 3 corners are shared to form 2-dimensional sheet. Just like a paper, one paper. 2-dimensional sheets. Example is clay. In soil you have seen. In soil, a small part, you can see that soil you will see, they will find very small particles will be there. Very small. Their length, breadth may be there, and height will be very less, negligible. Then here this example of sheet silicate is clay, CLAY, clay. Now next 6th type is a 3-dimensional silicate. Sheet is the example of 2-dimensional. Sheet is the example of 2-dimensional sheet. Okay, here it is a 3-dimensional silicate. Here all 4 corners. Silicate has tetrahedral, 4 corners are there. Then here in this case, in 3-dimensional silicate, all 4 corners are shared to form 3-dimensional network. 3-dimensional structure it will form. Length, breadth and height will be also there. Just like you can tell brick, length is there, breadth is there, height is also there. Like that way, here In three-dimensional silicates, name itself is three-dimensional silicate. Here, all four corners are shared to form three-dimensional network, means length, breadth, height, every direction. Then example of this three-dimensional silicate is quartz. QUARTZ. Question is asked. Whatever six type I have discussed silicate, all are asked in examination. Now I am going to discuss next point, imperfection or defects in crystalline solids. Imperfectness, imperfect, not perfect. Imperfectness oblique defects in crystalline solids. Actually, all points are important. You can't ignore any points. Okay, all are important. And now I am telling about what is the imperfectness. What is the imperfectness or defects in crystalline solids? Here, many defects are there. In crystalline solids. Means actually defects means departure from regular arrangement. Now suppose you wanted to make a cube. You might have seen the cube, correct? But now it is not in a correct way. Okay, sometimes it has inclined towards left, right, some deviation took place, or many atoms you have arranged in form of a square or pentagonal, hexagonal, correct? In many shapes are there. I told you maybe rectangle, triangular means tetragonal, square, hexagonal, pentagonal, like that way. In that way, you are arranging the atoms. After arranging the atoms, it will look like sometimes a sphere, sometimes a square, sometimes rectangle, just like a bricks. Correct? It will take the form, different form. Then if you can say they are arranged in a proper way, suppose you wanted to arrange in a brick form. If you have arranged all small atoms in a brick form or rectangular form, tetrahedral form, a sphere, correct, hexagonal, then if you arrange in a proper way, means generally you know that this ions also you can arrange cation, anion. You can cation, then anion, again cation, anion, again cation, anion, like that way. Everywhere it will be arranged in a proper way. Then that is a perfect. But sometimes it will arrange in other way. It will deviate from the original. It will deviate from the regular arrangement, or you can tell departure from regular arrangement. That is called defects in crystalline solid. Generally, crystal will be the solid form. Then that is called defects in crystalline solids. Generally, you will talk about the metals. In metals, you know that many atoms will be there. Many atoms will be there. And in NaCl structure, sodium chloride, potassium chloride, magnesium sulfate, calcium chloride, calcium sulfate, all big lump you are seeing. But you will see a small, then you will find all are NaCl are arranged in a proper way. Then just like a cube, NaCl, you will see that it is found in the form of a cubic structure. Then if it arranged in a proper way, all NaCl, Na plus Cl minus are arranged in a proper way, then there is no deviation from the regular arrangement. But if there is any departure from the regular arrangement, then that is called imperfections or defects. And now I am telling name of the defects. Just first example is Schottky defect, SCHO double TKY, Schottky defects. Second defect important is there, Frenkel defect, FRENKEL, Frenkel. All are the based on the name of scientist. Then first I told you Schottky defect, second Frenkel defect, correct? Then here what is actually Schottky defect? Then Schottky defect is that in which equal number of cation and anion are missing from their lattice sites. As a result, density decreases. Actually, somewhere cation and anions are missing. Then now what will happen? From somewhere cation and anions both are missing from their lattice sites. Then as a result, density decreases, because mass density is equal to mass by volume. Then volume will be volume will be the same. Volume will be the same, but mass will be less, because cation and anions are not there. Then cation mass is there, anion mass is there. Then there will be less mass. Then mass will be less, volume will be as it is. That's why density will decrease, mass by volume. Volume is same, but mass decreased in comparison to the earlier. That's why density decreases. Question is asked. Then this is called Schottky defects. Schottky defects. Now Frenkel defect. Frenkel defect. What is this? Then Frenkel defect is that in which cations are missing from their lattice sites and occupy interstitial sites. As a result, density remains unchanged. No change in density. Now why? Because from one place it is missing cation, positively charged, but now it went to the other places, and between the gap it went, because we can say cation, anion, everywhere it was arranged. Then cation from the one place it will move, and it will go to the in between the cation and anion other places. Other places it will adjust among the gap. That is actually, that is called interstitial sites. Gap, in that gap it will go. That is called interstitial sites. INTER, interstitial, STITIAL, interstitial site. Then here there is no change in mass. Volume is also as it is, because only from one place it went to the other place, but it is only there. As mass is the same, volume is the same, and there is no change in density. Density remains unchanged. Question is asked. Related to density only question is asked. Now next point I am going to discuss F centers. F centers. F means farbe. FARBE. Farbe, that is in a simple way it is written F, and farbe means color. Farbe means color. Then that is called F center. F centers. Then what is actually F centers? Then F centers are the sites where anions are missing. Now see the another problem. This is also defect. F centers. F centers are the sites where anions are missing and instead electrons are present. Now see, anions have negative charge, Anions have negative charge, but anions are missing, and in its place electron has come. This is the main things you understand. Anions are missing, and in its place electron is coming. Correct? Then F centers are the sites where anions are missing and instead electrons are present, and they are these electrons, they are responsible for color. Correct? Particularly these electrons are responsible for color. Correct? Electrons gone to the other places and its place electron has come. Correct? Then F centers are those sites where anions are missing and instead electrons are present. They are responsible for color. That's why it is called F centers. Now, next point is doping. Doping. What is doping? All things are now interesting. Whatever I will discuss now, all are very interesting. Then doping. What is the doping? Doping means incorporating a small amount of foreign impurities. Incorporating means mixing in a simple way. Mixing a small amount of foreign impurities. Knowingly you are mixing foreign impurities from the outside. In the crystal, pure crystal, you are mixing from the outside some atoms you will mix. Then that actually mixing is called incorporation. Incorporation. Then doping means incorporating a small amount of foreign impurities. What is the purpose? Why you are mixing? Why it is mixed? Now you listen. Then first you understand what will you mix. Then group 13, 14, 15, just to keep in mind. In periodic table, group 13, group 14 and group 15, you keep in mind. Then doping of group 14 elements. In group 14 elements, what are the elements present in group 14? Then it is the, you can say, important thing only I am telling you. Actually, you know what are the elements present in group 14. That is the carbon, silicon, germanium, stannous, lead. Correct? These are the member of group 14. Carbon, silicon, germanium, stannous and lead. Then out of these five, silicon and germanium are semiconductor. It is very, very important. All are important, but silicon and germanium are used in computer in the form of chips. Then here silicon and germanium you want to mix this germanium or silicon. You want to mix some things. What something means here what? Then these, I told you, metal from group 15, particularly in silicon and germanium, anyone you can consider. You want to mix some impurities. Then here impurities means atoms from either from 13 group or from 15 group. Correct? Either from 13 group or from 15 group. You want to mix in 14 group element, that is particularly for germanium and silicon, semiconductor. So, these both are called, silicon and germanium are called semiconductor. Other examples also there. Later on, I will tell you that also. Then here, that doping means incorporating, means mixing a small amounts of foreign impurities. Foreign impurities are here group 13, atoms of group 13 or atoms of group 14, 15. In the middle 14 is coming. Correct? Then from 13 or from 15 to group 14 metals, particularly silicon and germanium. Then these atoms are foreign impurities. Then doping means incorporating a small amount of foreign impurities. Doping of group 14 elements with group 15 elements gives rise to a excess electrons. Excess electrons, it will produce excess electrons. Whereas with group 13 elements, if you will mix 13 group 13 elements, if you will mix, then it will create group holes. From 13 group elements, if you will mix, then it will give rise to holes. Hole means positive and electron means negative. Hence in the first case, it will create negative charge. And in second case, when hole will be formed from the 13 group, if you will mix, then it will create hole, means positive charge. And from the 15th, if it will intermix, then it will create a negative charge, means electron will be there. Correct? Then negative and positive charge can be created by mixing it with 15 atoms from the 15 or atoms from 13 elements. Then both make actually group 14 elements semiconductor. By mixing, now it will become semiconductor. Actually, you know that there are three types. In periodic table, you are divided into three types. That is the metal, non-metal, metalloid. Metalloid means having character of both metal and non-metal. Means here metalloid means now they have properties for both. As you can say, it can be as a metal, means it can donate electron, and sometimes it can take electron also. That both character will be found in metalloid. Amphoteric, you know that amphoteric substance that will behave like this. They will behave like acid as well as base. Then here just this germanium silicons, I am telling you, they are actually non-conductor in real sense. But after mixing means after incorporation of a small amount of foreign impurities, it will work as a conductor. Not very good conductor, but semi means 50-50, you can tell. Their conductivity will increase. Metal conductivity will increase. For that purpose, doping is done. Mixing is done. Okay. Then here I told you that mixing is done either from group 15 sites or from 13 group elements. Their atoms are introduced. Then 15 group will atoms from 15 group will create a negative, and from 13 will create positive. Okay. Then both means 13 and 15 make group of 14 elements semiconductors. Then former means group 15. The former are called N-type. N means negative. A small N-type. Question is asked, what is the N-type? N means negative, because it is N is coming, means electrons are coming, which is negatively. That's why then when impurities is done from the 15, group 15, then that is called, that will form N-type, means negative charge flow. There will be flowing charge, it will form charge that will flow, means negative charge flows. And similarly, the latter what we have done from the 13, P-type. P means here positive holes created. Positive hole will move. Then that now you can see which was non-conductor, now it became conductor. Then it may become negative and positive. Positive means when it will get positive charge, means it will hole will move. And if it is negative, then it will, electron means negative, then negative charge will flow, means now it became conductor. It can this germanium and this silicon will function as a semiconductor. Question is asked. Okay. Then this I have told you what is the N type and P type. N type conductor, P type conductor, semiconductor. N means negative, P means positive. Okay. Now next point I am going to discuss, that is the regions for conductivity by solid. Regions for conductivity by solids. You see that copper, aluminum, copper wire, aluminum wire, they conduct electricity. Correct? Then what are their region? Cause I am telling you. Regions for conductivity by solids. The conductivity of metal is due to presence of mobile electrons. Actually, in metal there will be sea of electron. Many free electrons will be there in metal. Many. That's why SEAC, it is called sea of electron. Sea of electrons. The conductivity of metal is due to the presence of mobile electrons. Okay. The small conductivity of ionic solid. Ionic solid means negative and positive charge will be there. Then a small conductivity of ionic solid. Metal is in metal conductivity of metal is due to electrons, free electrons, mobile electrons. But in ionic solid, then a small conductivity of ionic solid in solid state is due to presence of defects, whereas large conductivity in solution. In solution also conductivity will be there. Then what is its reason? Then solution in conductivity is due to ions. Okay. Due to the ions. Conductivity in solution or in the molten state is due to flow of ions. Due to the flow of ions, there is conductivity of region for conductivity of solution is flow of ions, negative ion or positive ion. It flows, and due to that conductivity generated, means for the conductivity of solution, this flow of cation and anion is responsible, or in simple way, flow of ions. The conductivity of a semiconductor, what I discussed now, germanium and this silicon. The conductivity of a semiconductor is also due to presence of defects such as holes. Now another point I am going to discuss, that is a diamagnetic substance. There are many magnetic substances. First is diamagnetic, second is paramagnetic, third is ferromagnetic, fourth is antiferromagnetic. Correct? And next is ferrimagnetic. Then this I will tell you what are these. Then diamagnetic substances are those which are weakly repelled by the magnetic field. Correct? These are not magnetic. Diamagnetic means they are not magnetic. Okay. Diamagnetic substances are those which are weakly repelled by the magnetic field. They do not contain any unpaired electron, means fully paired. Diamagnetic means no unpaired, fully paired electrons. Okay, in orbital, each orbital will have two electrons, not unpaired. If it is unpaired, then it will show paramagnetic substance. Paramagnetic substances are those which are attracted by the magnetic field. Diamagnetic, it is repelled, but in paramagnetic, it is attracted by magnetic field. They contain unpaired electrons. Now, ferromagnetic substance. Ferromagnetic substances are those which show permanent magnetism, even in the absence of magnetic field. Examples are ferrous, cobalt, nickel, FeCO(Ni). These are the examples of ferromagnetic substance. Ferromagnetism decreases from iron to nickel. Means iron is more, you can say, ferromagnetic substance. Second is cobalt, third is nickel. It ferromagnetic properties decreases from iron to nickel. Iron has more quality, more you can say ferromagnetic substance. After that cobalt, third is the nickel. This is ferromagnetism decreases from iron to nickel. Okay, because the number of unpaired electron decreases. If more number of unpaired electrons are there, then more ferromagnetic. If it is less, then less. Okay, then FeCO(Ni), Fe is more, after that CO, and least is nickel. Now reverse of ferromagnetism is anti-ferromagnetic. Anti means it is opposite to ferro. Anti-ferromagnetic substances are those which are expected to possess paramagnetism or ferromagnetism on the basis of unpaired electrons, but actually possesses zero magnetic moment. Zero magnetic means expectation was there that it should behave like a paramagnetic or ferromagnetic, because unpaired electron was there, and unpaired electron is there, but its magnetic moment is zero. Means now it was expected, but it is not behaving like that. It is not behaving like paramagnetic or ferromagnetic. Correct? Then antiferromagnetic substances are those which are expected to possess paramagnetism or ferromagnetism on the basis of unpaired electrons, but actually possesses zero magnetic moment. That is, example is MnO, manganese oxide. Manganese oxide. This is due to the equal number of magnetic moments of the opposite direction. See, all have neutralized. It was there, unpaired were there, but all were in opposite. Due to equal number of magnetic moments in opposite direction, then all have cancelled. Unpaired was there, but in opposite direction. Then it is cancelled. Then now today I am stopping only here. Next class again other many terms are there. Then I will continue in next class. I think all important points will be finished. Then extra things I will tell. Then today I am stopping only here. Thank you.